Uh, well, thank you very much for letting me speak to you. I do not have any gory stories about people dying. In fact, I think the reason I went into geology was because when you hit rocks, they don't bleed, they don't scream, they don't gush, nothing bad happens. But I would like to talk to you about some of Wyoming's geologic secrets. Now, you're going to think this is silly because we don't have things that are secret about geology. We have things that are famous about geology, right? So everybody knows about Yellowstone, and in this corner of the world, you've got the Bear Lodge and Devil's Tower. What other famous scenery do we see here? Who knows what's in the upper right? Snowies. What about bottom right? Down near Lander. Red Canyon, just outside the Red Desert. So people, we talk a lot about our energy resources, but really our scenic resources are our second most important economic driver to the state with all the tourism we have. Of course, our energy resources are really important, and most of them are around this part of the state. So which one is not around this part of the state? And what do you figure that top left one is? Of Trona. Boy, you guys are sharp. Okay, well, I may be in trouble here because I may have nothing secret to tell you. But I'm going to try, okay? So here are the secret locations, and I'm going to start down by Laramie and work across. And you can see I had to pick ones that you wouldn't be familiar with. There are none near you. Not that there aren't some to talk about, but I had to find some that you didn't know. So we're going to start with Vidavoo. Now, how many people in this room have driven from Cheyenne to Laramie? Okay, so we're talking familiar ground here, right? These were the first real rocks that the territorial geologic surveys found when they left the east and they went out to explore the geology of the western U.S. Now, why do you suppose these were the very first rocks they came and saw as they went west? How did they travel? On the train. And where does the train go? Right across here. Now, part of the purpose of these surveys was to tell all about the wonderful geologic resources in the West so that Congress would give the survey more money to come back and look more at other places. So there was a great emphasis on promoting the geology. So when they got to Vidavoo area and saw the very first decent rocks, they drew pictures in engravings like this one with nice little people there in the foreground. And then the director of the survey said, this granite is wonderful. It's like Scottish syenite, cachet. And it's elegant and brighter than the Quincy granite. That's back in Massachusetts. So lots of promotion. One of the engravings that came back from this area, going from Cheyenne to Laramie, is this picture. Do you recognize this picture? This is Granite Canyon. This is where that road metal quarry is between Cheyenne and Laramie along the interstate. Well, apparently in 1870, it was glaciated and much more mountainous. So I thought, where in the heck is that picture from? I took the train from Cheyenne to Laramie. This is what I saw. And in fact, one of the famous Scottish geologists really wanted to see the Rocky Mountains, and so he came out on the train, and he said, I approached the crest of the Rocky Mountains. There was apparently a sign that said crest of the Rocky Mountains. He looked around with a feeling of incredulity for the peaks and crests that ought to have been there. Instead, there were just quaint knobs of pink granite. Well, actually, this pink granite is pretty cool, and it's the first secret. So here's a picture of this. It was called the Sherman Granite after Sherman Station, which is a ghost town. It was a train stop between Cheyenne and Laramie. Well, we've dated this rock, and it's 1.43 billion years old, so pretty decently old, and it's very pink. It's got more iron than most granites have. And it actually turns out to be different from granite that's almost anywhere else. It formed directly from the mantle, so deep in the earth. And you can see this because it's mixed with mafic basalt. So we've got the dark lavas that come out at Hawaii directly from the mantle, and then granites usually you think come from melting the crust, but these don't. And you can see in these pictures, which are right up in the Vidavoo area, all this mixture of dark and pink rock. Well, here's the secret. This rock, even though it's 1.4 billion years old, can be found in another part of Wyoming. And it's a young part of Wyoming. It's Yellowstone. So you all know, you know, it's not secret, that Yellowstone is a supervolcano, right? And that there's magma underground. That magma is the same kind of magma as at Vidavoo. And so here is a picture of Yellowstone Falls with all the pink rock. Here, when you go across the Snake River Plain following the hot spot that is now under Yellowstone, you see some of the black rock. And so the magma that's underneath Yellowstone today, when it solidifies, will look just like Vidavoo. So do you think the climbers at Vidavoo realize that they are basically climbing on what is underground Yellowstone? So that's the first secret, that the granite at Vidavoo is basically Yellowstone underground. When Yellowstone solidifies and all the stuff above is eroded, that's what you'll see. Okay, now we're just going to go a little bit farther north. So how many people have driven from Wheatland to Laramie through Sabile Canyon? Okay, so quite a few people. All right, so you might remember that it's just gray and black rock, basically. Well, I want to tell you a little bit about the woman who first mapped this rock. Her name was Katherine Fowler Billings, and she came from Boston. You can kind of tell that nice little lacy collar. But even though she's wearing the lacy collar for her passport picture here, she was a complete tomboy, and she was a rebel. And she was so rebellious that instead of going to college in New England, she went to the only college that her parents would allow her to go to that was outside of New England, Bryn Mawr. So she went to Pennsylvania. How daring. But that was just the beginning, because there she met a woman professor of geology who convinced her to go to graduate school. And to go to graduate school, you needed to have gone to a geologic field camp. Where do you go to geologic field camp if you're a girl? To the University of Wyoming, because we took girls. Why did we take girls? Maybe because we were the equality state, maybe because we needed the bodies. But anyway, so this young woman got to the University of Wyoming to field camp, and she drove that old car. She's looking kind of butch, isn't she? It's pretty interesting. And she got to the Medicine Bows where Doc Knight had built this old camp. And it was July, and there was snow. And she couldn't believe it. So she and a friend got on their swimsuits and started a snowball fight. Well, that was not the only trouble she got into. Doc Knight was very regimented about how, girls go this direction, boys go that direction. Drinking water happens up here, swimming happens down there. Well, she went swimming where you're supposed to get the drinking water. And so she had to be taught a lesson. And this is something we do not do in our field camp any longer. But Doc Knight showed off how to hog tie on her as punishment for having swum in the drinking water place. Well, she liked the experience so much she decided to do her PhD mapping the Laramie Range. And she had great adventures. She did not like snakes, however, and so she had to have target practice shooting snakes. And she decided this was the photo she would send to her mother. And I saw it. On the back it says, "Look at your daughter now." And the sad thing is her mother died only a few weeks after. This was the last picture she had of her daughter. But this woman, Kay, did a beautiful job. She had to make all the topographic map before she could even put the geology in it. And so when I arrived at the University of Wyoming, I actually called her up and said, I want to continue on with your work, and would you tell me about X and Y? And she said, "That was 70 years ago." And so she wrote an autobiography. It turned out to be her second autobiography about her life as a pioneering woman geologist. Well, that said, then we went on, my students and I have worked in this area that she started out mapping for many, many years. So she basically mapped all this way, I mean, a huge amount of territory. And she really got it right. We were able to add a lot of detail, date the rocks, and so here actually in red is where that Sherman granite was, the Yellowstone Underground. And here in blue is a very different kind of rock that's made almost entirely of plagioclase feldspar. It's actually the feldspar that's in my necklace, which she gave to me as a present, kind of a bond. Well, the rocks that have these minerals in them are spread all through North America, but the best place to see them is right in Sabile Canyon, because that's where they aren't all mashed and deformed by later events. And so here's an example of what you can see. The rock is almost entirely made of this single mineral, feldspar, and it often has this play of colors that you see in my necklace and then also in this picture. And my students in classes call them zips, zoned iridescent plagioclase. Oh, I found a zip. Come over here. It's zippy over here. You know, that's what goes on at the University of Wyoming. Anyway, there's one other place where rocks like this occur in great abundance, and it is the highlands of the moon. And so here's the second secret. You may have always wondered about the Wyoming Tourism slogan that we used for quite a few years. Perfectly sensible, right? Okay, so third one. We're going to go to the Granite Mountains. Okay, you know where the Granite Mountains are, right? If you drive from Casper to Lander, you go through this fairly subdued country. It's, they're named the Granite Mountains, and it's a good thing. They are composed of granite. This doesn't always happen that way. If you go to buy a countertop at the countertop store, they'll sell you what they're calling granite, and it isn't granite at all, but it's either granite or marble. So anyway, whoever named the Granite Mountains knew more than the countertop people. But you'll have to admit that the topography is pretty subdued, right? So this is what you see if you're anywhere in the area of Muddy Gap, Jeffrey City, that beautiful area along the Oregon Trail. Well, I think it's wonderful. But when you're there and you look west, you know, you see the majestic Wind River Range in the distance, right? And the Wind River Range is also made of granite, but it's much more spectacular. So what went on? Well, the man who figured this puzzle out was Dave Love, who many of you will know. He's the kind of the subject of John McPhee's book, Rising from the Plains, that was published in the early 80s. He was a geologist who lived and worked out of Laramie, Wyoming for the USGS for his entire career, born and raised in Wyoming. He, around here, he is the person who discovered the uranium in the southern Powder River Basin that's now being mined in situ. He was the discoverer. But what his contribution in the Granite Mountains was, is to recognize that there are two major faults. Okay, so now maybe we need to have a little orientation here. So this is Muddy Gap. And here we follow the highway up to Casper. And here here's Jeffrey City, and then we're going over toward Lander. Okay? So there are these two major faults, and the area in between, which includes the Granite Mountains, dropped down. And he spent a lot of time looking at the age of the sediments that filled up this trough and was able to determine that the rocks dropped down about 5 million years ago, and they kept going down in pulses until about 2 million years ago. And he was always a little hesitant to say how much downdrop there was, but if you look at his maps, it looks like about 5,000 feet. Well, it's like a mile, right? It went down a mile. So if you factor that in, here's Lankin Dome, which is along the Sweetwater River. It's about 7,700 feet tall. What are the tallest mountains in the winds? 12, 13, all those high peaks. So this would have been just as high as the Wind River Mountains before it dropped down. So what do you call that? Well, I think we should call it a geologic tragedy. And what do you think Dave Love would have said to that? Well, he probably wouldn't have said a thing. He probably would have showed you his favorite self-portrait. That is the back end of a horse. Okay. Should we do one more? Do we have time? Okay. So we're gonna do the last secret is one you're gonna think, well, there's nothing secret because everybody knows the Tetons. But there's actually something that very few people do know about the Tetons, and you are soon to be in the loop here. So let's have a look. The Tetons are kind of a conundrum. Here's where they're located, you know. And they're within an area of very old rocks. And appropriately enough, it's called the Wyoming Province. You are in the Wyoming Province. I think it's something of a geologic tragedy of a type that actually Laramie is not in the Wyoming Province. It's just south. This is hardly fair. I don't know what we're going to do about it. But anyway, so all the old rocks are in this area, and the only place you can actually walk on the old rocks is in the mountains, because that's where the mountains have been brought up. All the young rocks have been eroded off, and you can walk on the old stuff. Well, that's what's happened in the Tetons. The Tetons are one of our youngest mountain ranges in the sense that they're still going up. Here, let's see, we're looking south along Jackson Lake in this picture in the top. And the fault that along which they're being brought up today runs right along the front here. And that's this fault here. But there's actually an older one that pushed them up just like the other mountain ranges in Wyoming about 50 million years ago. And then more recently, you've got this kind of trapdoor thing where it's going like this. So the Tetons are still actively going up. And that's why they're so rugged and spectacular. But because they're going up, then all the stuff on top is eroding away, and we can walk on the old rocks. Well, it takes a pretty rugged individual to map these rugged peaks. And it turns out that the mapping was done by a friend of Dave Love's named Jack Reed. And he was a great climber, as you can see from the picture on the lower right. And he was in his 30s. I mean, I do have to tell myself this when I'm struggling around in there. He was much younger than I. But he went everywhere, and he didn't leave anything unturned. And so he worked on all the high peaks. And actually, Dave Love did all the low country, the younger rocks in the low country, and they prepared a map. And from that map, I could tell where I wanted to go work. Because the southern part where the cathedral peaks are is down here where it's pink. And there are some late Archean granites that actually came in and kind of obliterated all the even older history. So it kind of wrecked it as far as looking for the oldest rocks. So we have been focusing up here where there are two colors that were mapped by Jack Reed. There were gneisses, which are deformed rocks, and then granite, light-colored, leucogranite, light-colored granite. He distinguished those two different units. And we've been able to subdivide those a little more. And so here you can see our students on the outcrop. This picture actually really disturbs me because here are all the students standing around while I am doing the work. It's like, how did that happen? But what we were able to find is that some of these old rocks, you can kind of tell already, they're pretty complicated, used to be mudstones. I mean, these are rocks that started their lives as ground-up sediment, fine-grained sediment, and basalt, so lava flows. So these were rocks that were on the surface of the earth. They had to have been transported down deep into the earth because now they have minerals like this bluish one called kyanite that only exist at high pressures. And these basalts got hot enough to melt. And basalts actually have a very high melting temperature. So we actually are able to specify the temperatures and pressures at which these mudstones got. And they were pushed down 40 kilometers, so what's that, 25 miles? Way down. And 1700 degrees Fahrenheit, way hot. So somehow we had a situation where things that were on the Earth's surface went way down. And then, by looking at some of these rocks under the microscope, we can see that the high pressure minerals, which are here in this golden color, now look very ratty because they were brought up closer to the surface where they're no longer stable. And different minerals are growing. So that tells us a little more information. And it tells us that the rocks that had been down, 40 kilometers then got brought closer to the surface. Pressure is high pressure here, and here's the surface down here. So rocks that were deep got brought closer to the surface. Now there's a second group of rocks that never seemed to get any deeper than this. So somehow we have two blocks with different histories that were brought together. They're different compositions. So we had the mudstones and the lavas. And then over here we have more granites that were all mucked up. But very different rocks. And from different isotopic signatures, we can tell that they came from different sources. The muds came from some old continent. These rocks came from fairly young crust. So somehow we have two blocks of rock that were brought together, and one of them went way down deep. And then they were glued together after that. We've been able to, this is pretty involved secret, isn't it? We've been able to determine the timing of all this. So this happened about 2.7 billion years ago, that the rocks got buried deeply, glued to the other block. The other block actually started to melt and made these light-colored granites, all within about 15 million years. Well, the only modern analog that explains all these things happening together is the Himalayas. And so we have proposed that what is exposed in the core of the Tetons is a record of the very earliest continent-continent collision. So like today, you've got Asia and India ramming into each other, and India is being pushed down below, and it's melting, and it makes these granites and high-pressure rocks, same assemblages. That happened back 2.7 billion years ago in Wyoming. It's the very oldest known continent-continent collision. And it's significant because it says that that far back in Earth history, the crust was thick enough and strong enough that it didn't just crumple. It actually was rigid and could collide and one plate be deeply buried. So the Tetons are the oldest known Himalayan mountain belt. So you've got it. Vitavu is Yellowstone Underground. Sibyl Canyon is like no place on Earth. The Granite Mountains are a geologic tragedy, and the Tetons are home to the Earth's very first Himalayas. And that's it. No death!
We have time for questions if you'd like to direct them to Dr. Frost. See one here in the back.
Okay.
I was reading the other day about Yellowstone being associated with possibly with a fragment of the Farallon plate riding under, and deflection off of the plate fragment.
Okay, well, so the Farallon plate is a plate that was in the Pacific Ocean that has been subducted now and has apparently gone well under Western North America. And usually that is attributed or given the cause of why our mountain ranges exist. Now, most of our mountains came up about 50 million years ago. You know, the Laramie Range, the Bighorns, the Winds, and that's usually connected to the Farallon plate because at that time it was just underneath and it would have been just pushing so that these these thick thrusts could happen. Yellowstone, as you know, is usually associated with a hot spot like under Hawaii. It's possible that there could be some edge effect, that's about where the edge of the Farallon plate would be, and that might actually be able to focus the mantle upwelling that we associate with the hot spot. But that would be my best guess, not knowing the specifics of what you read.
Well, I guess it was a UC San Diego survey that's going on right now where they're doing seismic surveys across the
Right,
country.
yeah.
And tying in seismic networks, I would guess.
Yeah, it is pretty amazing how well we can image these plates far from where they originally go into the subsurface. And it is true that we can track that Farallon plate well inboard. But I'm just guessing that it'd have to be that northern edge that would have.
And is there a décollement on the Tetons that you're seeing? That you see a lot of like, twisted rock and.
The modern uplift is fairly brittle at the surface. But of course, what it's doing is bringing up these really old rocks that have had horribly contorted and extensive histories. So the folding is actually very complex up there. The Laramide thrust, the Buck Mountain Fault, it has something of a décollement. But the old rocks have far more deformations reported in them. Yes.
The surveyors that you mentioned, have there been like modern surveys done just to like double check what they've done? Because their process was like with a donkey or chain, right? Isn't that right? Like
Well, it's amazing how much we depend on those original surveys because they didn't have nearly as many tools. I mean, they didn't have a seismic network array. And so they only had really their powers of observation. And so in many ways, their work they were more exhaustive in their observations, and we really have built on those results.
They were strong and they were accurate.
They were very good, yeah. In fact, Jack Reed, who did the mapping in the Tetons, you just have to simplify when you make a map. You lump things in. And he was talking about these light-colored granites. And I looked in the map key that he had written, and he said, well, maybe I should have broken out a second type of granite. Well, I had just figured out there were two types of granite. Nothing new at all. He had already figured it out. He just hadn't broken it out on the map. So I think a lot of that pioneering work is really, really good. And unfortunately, it's not work that we can get paid to do. I mean, funding agencies want problem-driven science. Holly's back there. Hypothesis-driven science. They don't want just exploratory. Let's go map what's there. So we really do rely on those older good workers.
Could I ask you to just unpack this a little bit for a minute? If we're having Himalayan Tetons, and we're modeling it on the Indian subcontinent plate coming in, does that mean that Wyoming is the edge of we're the edge of two continents coming together?
We were 2.7 billion years ago. See, this is the hard part.
Right.
And so I showed you that map of the Wyoming province. And what we don't know exactly is how big it was. It's bigger than what we see today because it used to extend farther south and it rifted away. I showed you that picture of the Snowy Range with all that white colored rock. That's an old beach. That's a 1.7 billion-year-old beach. The old crust had rifted away. This Colorado is just an ocean. And so we don't know where that stuff went. Here are the Tetons. That collision says that at 2.7 billion years, some block probably hit the rest of the Wyoming province. But it's actually very hard. All this is covered with young lava. So it's actually quite difficult to know how far it even goes. And then out here in Idaho, this is the edge of the old continent. And again, whatever was there has rifted away. And there's new young stuff jammed on now. Old and new in geologic terms, of course.
Thank you very
Yeah,
much, Karen.
thank you.